Here's a picture of a Foucault pendulum. I don't believe we have a big one here in Toronto, but you see them around. If you go to things like the Smithsonian, Exploratorium in San Francisco has one, but what it is, also there's one at the Griffith Observatory in Los Angeles. So it's a pendulum, which just means it's a mass that's on a very long string, and it's allowed to swing back and forth. And a Foucault pendulum is one that is allowed to rotate in any direction. So it just can rotate any way it wants. But it wants to wants to oscillate in any direction, but it could even go around in a circle. But they set it up and they let it go back and forth. And what you find is that it does this thing where it swings around. This is zoomed in, but or it goes around like that once every 24 hours. If you watch it knock over these pegs, in 24 hours its plane of oscillation turns around once every 24 hours. So, of course, what's really happening is that its plane of oscillation is fixed in space. But the Earth is rotating beneath that thing every 24 hours. And so this is a proof that the Earth is actually rotating around. Every 24 hours we do this, and the Foucault pendulum just stays in the same plane. Yes?
What if you put the pendulum at the equator and then you oscillate it in the direction of the Earth's rotation?
Yeah, this doesn't work on the equator. You have to be far from the equator. I don't know how far you can get a Foucault pendulum to the equator, but yeah, the equator doesn't rotate. That's a really good point. So this is done in San Francisco or the Smithsonian's in Washington, D.C. It's always where you're it would be perfect on the North Pole or the South Pole. If you're not on the North Pole or the South Pole, it still goes around once every 24 hours, though. It's a really good point. But on the equator, it doesn't work. Okay, so the book does this thing where it compares uniform circular motion to simple harmonic motion. And this gets back into that whole business. Remember where I almost fell off my chair because my kludge turned into a cosine? So let's just talk about that a little bit. And we'll do a little review, and I'll try to do it actually on the PowerPoint here, so bear with me. So uniform circular motion is going to look like this. You've got an object that's going on a circular path. Maybe here it is. And it's got constant angular speed, omega. Okay? We can define an xy axis. So there's there's y, there's x. So define x and y, where the origin is at the center of the circle. We can also define, if we want, the radius is a, capital A. That's going to be just for fun. And then we can use kinematics of circular motion to get that theta final equals theta initial plus omega times t. This is one of our, I think she actually had just theta equals theta 0 plus omega t. So what we've got is omega is 2 pi divided by the period t. T is the period of the motion. And 2 pi is how many radians it goes through once every circle it goes around the circular path. And if you set theta 0 equals 0, it starts on the x-axis. Then you get theta is equal to 2 pi divided by the period times lowercase t. And if you look at this triangle and do your SOHCAHTOA, and here's your theta, and here's y, and here's x, and here's that radius a, then you get that x is equal to cosine, it's a, the hypotenuse, a, times cosine of 2 pi over capital T times t. Which is, I mean, again, and if you have, here's a wall, and here's a spring, and here's a mass m, and this is k, and this is m, and you define x equals 0 to be the equilibrium position, so there's your x, then a sub x is equal to negative some constant, times x, it was k over m or something like that. Then the trial solution that they tell you in math class is that x is equal to a times the cosine of 2 pi over the period times lowercase t, where a is, they say, some constant. So I'm just going to, again, I don't really know how to elaborate on this except to say, like, wow, it's the same mathematical solution, even though these are unrelated physical phenomenons. In one case, perhaps you have a coin that is sitting on a turntable, a disk that is rotating with constant angular speed. The coin goes round and round. And if you track just the x position of that, it goes back and forth with this cosine. The other one is that you've got a mouse on a spring. But mathematically, exact same description. And like I say, at 30 years in this business, I've never had anyone really explain to me why this works this way. It can't be a coincidence, right? I'm just going to take it as being a solution. So that's enough said about that. So we talked a little bit about this Vmax and Amax, and what was really weird is that the maximum speed happened at equilibrium, where there's zero force. Does that make sense? When you've got something oscillating back and forth, again, I'll try to get this right here. When it goes through its equilibrium position, for an instant, the force is equal to 0, so the acceleration is equal to 0, but it's going as fast as it's ever going to go. So it's kind of like, if you're away from equilibrium, it starts at 0 when it gets to its maximum, how far it's gone away from its equilibrium, and then it speeds up, speeds up, speeds up, speeds up, speeds up, passes through equilibrium, then slows down, slows down, slows down, slows down. So it changes from speeding up to slowing down. That's when the acceleration changes from one sign to the other sign. And that means it goes through 0. Anyway, if you look at this equation, x equals a times cosine of some stuff, we know that that cosine just varies between +1 and -1. So that means that x max is equal to a, the amplitude. Okay, so cosine, whoop, just want to make a note here, whoop. Cosine of theta has a maximum of 1, right? And the other thing is that we have these crazy equations, and I didn't really explain to you where these came from, but I think I might have given you a glimpse of them. Anyway, just believe it. The V turns out to be negative sign. We tried to kind of plot that. I don't know if you noticed that when I did those plots. I had x was a cosine. So V started off, the slope started off at 0, but then it started becoming negative as it went down. So it's a negative times sine. And there's a thing out here which has to convert this A in meters to meters per second. So you have to divide by something with seconds in it. Turns out it's 2 pi over capital T. And so Vmax, and this is the equation that's really useful to have in your aid sheet, is equal to 2 times pi times A divided by capital T. So I'll put that one on there. Because the sine has a minimum of -1. Make sense? And then also A maximum is equal to, I think it's 4 times pi squared times A divided by T squared. And you can do the units check there. A is in meters. 4 pi squared is dimensionless, and capital T is in seconds, so this is meters per second squared. So I think that's okay. So in all these cases, A is the amplitude in meters, and capital T is the period in seconds. Okay. Let's do a learning catalytics. This is showing an astronaut who's sitting in a special chair called the Body Mass Measurement Device chair. So if you're an astronaut, there are various health problems that you can experience if you spend too much time in space. Most of the health problems are related to the fact that you're just in microgravity. So We don't know it, but we're exercising all the time because we're in this 9.8 meters per second squared. If you're up there in space and you're floating around all day, your muscles tend to atrophy, and also your bone mass starts to decrease. And so you have to do a lot of exercise, and you have to try to keep in shape. And so they have to measure their mass. They also can't just stand on a bathroom scale because it always reads 0 because there's no gravity. So what they do is they have a chair that goes shaky, shaky, and then they sit in it and see what happens. So this is your question. If it shakes when it's empty at 1.2 seconds, what do you think is going to happen if this lady sits in it? I'll give you a minute to chat about that. Yeah, I think it's going to be more. Okay, and again, what I think the whole thing here is it's 2 pi times m over k. Same spring, but now we've increased the mass because we've added a person to that. That's going to slow down the period. Okay, and I want to do an actual example problem with that. The body mass measurement device chair has an empty mass of 32 kilograms. So I'm going to say ME is empty mass, which is 32 kilograms. And it has a vibrational period of 1.2 seconds when it's empty. When an astronaut sits on the chair, the period changes to 2.1 seconds. Gets a little longer. That makes sense. And the question is, determine the mass of the astronaut. So I can also define MF is the mass of the full chair. And then, and so if it's empty, this is sort of sketchy here, you've got some wall, hopefully it's attached to the rest of the space station, something that's much more massive than the chair or the astronaut. It's got some spring constant K, and there's the chair, ME, and the TE, empty here, is 1.2 seconds. If it's full, then same sort of thing, same spring, so same spring constant, okay. But you'll have now MF, T full is equal to 2.1 seconds, and it's find MA is the mass of the astronaut. Okay, and that's your question mark. And so I'm going to use this idea that mass of the astronaut is going to be the mass of the full chair minus the mass of the empty chair. So I can do that at the end. Let's zoom this in a little bit, right? Sorry, it's so small. Better? It's be hard to see from the back, but okay. So what I'm going to use here is that the T of the empty chair, I'm just going to use 2 pi times the square root of ME over MK. I'm going to solve for K because I think I actually have everything. I have the mass of the empty chair and I have the period of the empty chair, so I can just rearrange and solve for K. And then I'm going to use that T sub F is equal to 2 pi times the mass of the full chair divided by K. And I'm going to solve for M sub F and then plug in. And then plug in my value of K. Okay, so I think that is actually all the physics you need to know, and the rest is math. Make sense? 2 equations, sort of 2 unknowns, we're going to eliminate the K. Want to do it? I'm just going to solve for K, I think it's even better. So I'm going to square both of these things. So let's square both sides. I'm going to get TE squared is equal to, there's going to be 2 pi squared, which is a 4 pi squared times M sub E over K. So rearranging, I've got K is equal to M empty times 4 pi squared divided by TE squared. So it's going to be 32 kilograms times 4 times pi squared divided by 1.2 squared. So I got the K is equal to 877.3, and the units are just going to be newtons per meter. It's whatever the SI units of K are supposed to be. Okay. And then same sort of thing. I'm going to square both sides of this one, and we get T final squared equals 4 pi squared square root, not square root, sorry, get rid of that square root, m full divided by K. Solve that for m full is equal to T final squared divided by 4 pi squared times K. So there's a 2.1 squared divided by the 4 times pi squared, and times it by the 877.3. Oops, I'm off the... sorry. Hey, Harlow, you're off the bottom of the page. Thank you. You couldn't see that? I times it all together, and I got that m final is equal to 98 kilograms. So the mass of the astronaut is equal to 98 minus 32. I got 66 kilograms. And then, I don't actually know if that sounds good, but I know that there's 2.2 pounds per kilogram. So that means that the mass of the astronaut is about 150 pounds. So that's okay. That's my rather shameful Canadian units check. It's like converted it to American, and then it made sense. Okay. So that's that. Yes, question? That was my evaluate. I converted it to pounds. Sound good? Sounds about right, right? About the right mass. So 66 is the answer, 150 pounds is the evaluate. All right, so next thing I want to do, I want to stay on the dot cam for a little bit. I'm going to move this over. Put that there. See if we can get another. We have to zoom out, unfortunately. Okay, let's just do it like this. Sorry. I will scan it immediately after class. First thing I'll do is go to my scanner. Here's a new question for you. What is the total energy of a mass on a spring as a function of time? This actually is not as hard as you might think, because we already know an equation for kinetic energy, and we already know the energy of a spring. So what we can do is just say, here's a spring, here's a mass. We'll have, let's just say x is equal to a times cosine of 2 pi over capital T times t. And we have the v is equal to negative 2 pi a over capital T times sine of 2 pi over capital T times t. The energy is going to be the kinetic energy of the mass plus the potential energy of the spring. So the energy is just going to be 1/2 mv squared plus 1/2 k times x squared. So I'm just going to take this value of v and plug it in right here. And I'm going to take this value of x and I'm going to plug it in right here. Now you might say to yourself, Jason, what are you doing? Don't do it, man! But I'm going to do it, okay? I'm doing it. That's exactly what my friend said to me when I was at that cliff at Thetis Lake, and there was like a, don't do it, man. But I just ran, I jumped right off that thing. Okay. 1/2 m times, I better have a big bracket, negative 2. So, I've done this before. It's going to be okay. Okay, you're not going to believe how much this sucker is going to simplify. But it takes a little while to get there. So I've got another bracket. Let's make this a square bracket. 2 pi over t times t squared plus 1/2 times k, open a square bracket, a times cosine of 2 pi over capital T times t, all squared. Simple. I say it with an evil laugh. No. Now I'm going to do a trick, which is, remember this cap, what I've got is a period here, which I don't like. It's kind of already outside. So I'm going to recall that the period is equal to 2 pi times the square root of m divided by k. So, this is going to make it look even worse for a minute, but then it's going to get better. So, E is equal to 1/2 m, let's open a square bracket, negative 2 pi divided by 2 pi times the square root of k over m. I've divided by this thingy, and look at that, it's my first simplification of the day. Anyway, let's not get excited yet. Times a times sine of 2 pi over t, don't forget the little lowercase t, squared, and then plus 1/2 k times a, this one didn't simplify much, so I'll just write it again, 2 pi over t squared. Okay. What else can I do? Okay, so the next thing I can do is pull out the constants and make them squared. Let's do that. So E is equal to, can you still see what I'm doing? Yeah. It's going to be 1/2 m. I'm going to pull up the square root k over m. It just becomes k over m because I was squaring the square root. And pull out the a, and I got an a squared. And then my square bracket is just becoming sine 2 pi t over t all squared. And then plus, I can pull out that a squared, and I got 1/2 k times a squared times cosine of 2 pi over t, lowercase t, all squared. What's next? Oh yeah, you guys are going to love this. So I got now, look, they both, so there's a cancellation here. M cancels with the m. Mass is canceled. So what I've got is they're both 1/2 ka squared. So E is equal to 1/2 k times a squared times sine squared of some thingy plus cos squared of some thingy. So now I have to push this to the left a little bit. And I'm going to say recall, right here. Recall trig identity, which is that sine squared theta plus cos squared theta equals, anybody know? This entire thingy equals 1. All right, so I told you this was going to simplify. It's E equals 1/2 ka squared. So you thought I was crazy. So I would just say that this is a surprising result. So both k and u sub s are always varying. Yet k plus u sub s is a constant. Okay, if someone had told me that before I started, I just never would have believed them. And yet there it is. I find simple harmonic motion to just be full of surprises. So there it is. And this is what it looks like. Sorry. You can do it. It's just math. The way it looks like graphically is that the kinetic energy is the green line and the potential energy is the blue line. One of them is cos squared and one of them is sine squared. Turns out when you add them up, you get a constant. And so somehow it's sloshing back and forth. And we have a graph of that, which is that if this mass is over here at a position displacement of negative a, then the spring has potential energy 1/2 ka squared, but it's at rest because it was going to the left and it's going to be going to the right, so it has to stop for a second. So that's its total energy at that moment. If it's at the equilibrium position, then it's going really fast. V max is that. And so what you can see right here, which isn't really obvious, but it turns out that 1/2 m times V max squared is going to have to be equal to 1/2 k times a squared. And that's kind of on the next graph there. And so then, again, if it's at positive displacement A plus A, then that's where the spring has all the potential energy, but it's momentarily at rest because it's going from going to the right to turning around, going to the left again. So that's how that works. Looks like that, and again, you can see it right up here. You've got 1/2 mv squared, that's a variable. 1/2 kx squared, that's a variable. When you add them up, you get a constant, and there's two ways of expressing the constant: 1/2 ka squared or 1/2 m times v max squared. Okay, we're just cooking along here. Oh yeah, and this is another way of looking at it, is this potential energy curve U sub s is 1/2 kx squared, is like a parabola. And so if you're used to, from chemistry or something like that, looking at these potential energy curves, then you're going to have a stable point at this equilibrium, and it's going to oscillate around that stable point. And the amount that it oscillates is set by the total energy, which is the total energy. So the kinetic energy is always the difference between this red line and the blue line. So it means it's going fast as it's going between here. It never gets outside these points because that would require negative kinetic energy, and that's not possible. So these are called the turning points where they turn around. All right. Yeah, so you can rearrange this to actually solve out for the Vmax in terms of K and M and the amplitude. And what it means conceptually is that if you have just a particular spring and a particular amplitude and you get a more massive cart, it's going to move slower. If you have the same cart but then you go to a stiffer spring, then it's going to move faster. That's basically all that is. And then this tip, which we're going to talk about next class, I guess on Wednesday, is that in the above discussion, we neglected the interactions of the system with the surface of the track and with the air. These are dissipative forces like friction. So these would both do negative work on the system and gradually decrease its energy. We're neglecting that in all this simple harmonic motion talk. So let's do definitely time for learning catalytics. By what factor must we increase the amplitude of the vibration of an object at the end of a spring in order to double its maximum speed? Think about that calmly, and then turn to your neighbor and discuss in a minute. Whoops. So there's a couple ways of looking at this. The one that I like to be, so the way I looked at it was just the fact that V max, this was on my aid sheet, is 2 pi over T times A, where T is fixed. So you can double the amplitude, but T is still going to be the 2 pi times m over k, right? Set by the properties of the system. So that's one way of looking at that. Let's do another quick one. By what factor do you have to increase the amplitude if you want to double the total energy of the system? Okay. You actually have to increase the amplitude by a square root of 2 because the total energy is 1/2 times k times a squared, right? Amplitude squared. Any questions about that? Ready to do pendulum? I think I may have promised somebody at some point we were done with torque, but I lied. Because it comes up. A little bit more torque. And that is because, so here's a pendulum, there's a mass on the end of a string. And what's interesting about this string is that it actually pushes as well as pulls. So I can go upside down. So I can go like this. Whee! So anyway, the idea is that if if you go fast enough, and I always wanted to do this in the swing when I was a kid at the playground, is I wanted to, go right around. But I never could do it because I always got the bumps at some point. Anyway, it's still a problem. You go, I don't know, I think it's because you can't get it to push because it's a chain. So when you go up here, you just go bump and then it really hurts. Have you experienced this? Anyway, you have, yeah. So this is what every kid wants to do, like, wee, wow, go right. It doesn't work, okay. And it would just wrap up the chain pretty quick anyway. But it's circular motion, that's my point. And the rotation axis is right down the center. So whether you think it is or not, I'm telling you that a pendulum is a kind of circular motion, so maybe we should use torque. And I'm going to assume that the rotation axis is up here, and I'm going to define pluses counterclockwise. It's good to review this stuff anyways because we have a final exam coming up, and that's certainly going to cover chapters 8 and 9, right? So let's review it. Sorry about lying. So let's do a force diagram. It's actually not that hard because it's really just a point mass. It looks like this. You've got the tension going up. Oh, I'm going to use capital T for the tension. Yeah, so it's not the period now, it's the tension. Sorry about that. We're using the same letters for two different things. And you've got mg going down. So I would just say that the torque from the tension is 0. Why? Because I think if you take the line of the tension, if this is T, it's going to go right up through the rotation axis that goes along the string. So tension cannot have any torque. So all of the torque, which is causing this pendulum to swing, is just coming from the gravity and that angle. Because T, I guess, points toward the rotation axis. So the theta is 0. So what you've got is you've got mg like this. You've got your L vector, which is like this, and you've got a theta between them. So the torque here, the sum of all the torques is just from mg. It's going to be mg times L times sine of theta. So that's the answer, as it turns out. All right, so now I'm going to go do some more math. I'm tired of writing on the screen, so I'm just going to, I typed it up. Ready? So it's this, mgl times sine theta. I'm now going to do what's called the small angle approximation, which says sine theta, if you use radians, is approximately equal to theta. Surprising, but true. And if you ever have your calculator set into radians mode, then you can try it for like 0.01. You do a sine of it, you also get 0.01. So instead of doing the net torque is equal to mg L sine theta, I'm just going to say the net torque is mg times L times theta. So I just disturb it a little bit. This doesn't work if I use theta initial as like pi over 2 or something. Or if I started from the top, it's definitely not going to be a simple harmonic motion. It's just going to sit there if I do it right at the top. So you just disturb it a little bit by less than about 10 degrees. And then you get that alpha, which is the slope of a theta versus t graph, is equal to negative some constant times theta. So all that stuff we did with the Excel and the kludge and the blah, 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 it's going to work for this. Except instead of x, I have theta, and instead of a, I have alpha. And instead of k over m, I have mg L over I. So that means that the period, instead of 2 pi square root m over k, I'm going to have, by analogy, 2 pi times this thingy upside down. Just I over mgl. So I'm solving this by analogy with mass on the spring, because I've got a similar looking equation. Okay? If you say that sine theta is theta equals theta. And then the other thing we can do is, because we know rotational inertia for a point mass, that's at a constant distance, L, is just ml squared. So we can plug in ml squared, and then the L squareds cancel the L, the M cancels the M cancels, and you just get square root L over G. That's it. I can write it down again, just in case you missed it. Let's do a learning catalytics. Let's write it down right here. T is equal to 2 pi square root L over G. Two pendula have the same length, but a different mass, which has, so the force of gravity is a lot bigger on the more massive one, so which has the longer period? Yeah, it's not. So like C? Again, it doesn't depend on the mass. The mass is canceled out. And I want to set this up, but I'm having a hard time with my masses there. So let's do another quick one. Oops. So this is actually showing, do I have another one? I do. Mass in a spring versus a pendulum. They both have a condition actually for simple harmonic motion. For a pendulum, we said that it has to have small angles so that sine theta equals theta, and that's approximately equal to. There's also a condition of small oscillations for a mass in a spring. You may not have even really thought about it before, but I don't know if you, I mean, we've assumed that Hooke's law works for the spring. So if you overstretch a spring, then I guess Hooke's law is no longer obeyed, and then it won't work anymore. So you won't have simple harmonic motion. That makes sense? F equals kx only works for small stretchiness or compression of a spring. If you ever had a slinky and you overstretched it on Christmas morning, the first thing you do, you destroy your slinky. It's no longer obeying Hooke's law if you stretch it too much. So, and then if you obey simple harmonic motion, then the period of mass in a spring is 2 pi square root m over k. For pendulum, it's 2 pi square root L over g. And again, what I'm going to try to do, if I can do this, I wanted to hook this on here, but it's just too small of a little knot. I don't have Pius here to help me. Maybe I can do it. I did it. Okay. So here's two masses. They are the same length, but this one is a 200 gram. This is a 100 gram. I pull it to the side, and they oscillate together, sort of, about. I don't think they're quite the same length, but it's certainly not a factor of 2 different. It is a little different, for sure. But for a couple of swings anyways, hopefully you believe me, okay? But if you have a different length pendulum, like this one, and let's get another small one, for example, beside here. And again, it's getting it through this thing which destroys my life. There it is. Okay. So let's compare these two same masses. Pull them. Okay, you go down here. Release it. Okay. This one's much shorter period because the length is much shorter. Okay, shorter period, sorry, shorter length, shorter period. Okay, and then we could do masses on a spring as well. And again, I'm trying to put my demos over here so that, I don't know if you guys can, how's it going over there, you guys? Can you see me? You see any of these? No? Not helping? I'm trying to put it closer to your video camera. Like I said, there was lots of seats. There's some right up here. They don't care. They like the room. They like to stretch their feet out over there. These are, well, this is just two masses that are same mass, same spring. You release them, they oscillate together. If you do more mass increase the mass, what's it going to do to the period? Whoa. Okay, so first thing is that the equilibrium position is way down there. Ready? Here we go. Oh, yeah, mass is on the top. Greater mass, so greater period. And then if I want to compare what happens to K, I have to have a spring with a different spring constant, and I happen to have one of those. This is a much stiffer spring than these ones. So and you can tell even that by if I take this mass, which is 100 grams, and I hang on here, it goes way down. So that's a not very stiff spring. This one, I hang it just goes down a little bit. So this is a higher value of K. If I release it, watch them oscillate. That has a much smaller period because the K is on the bottom. No? Can't see it? You can see it? Okay. Okay, good. All right, guys. Okay. Now that we're learning catalytics, last one. Again, you can tell I spent a lot of time in the playground. So you're in a swing, and if you sit on the swing, you have some period. Okay? If you stand on the swing, does the period get greater? Does it stay the same? Or does the period get smaller? Give you a minute. Okay. See, things are pretty split over here. So I'm going to stop it. So we're thinking, a lot of people are thinking smaller. So here's the way I'm thinking of it. You've got the top of the swing here. Let's try to draw it. So let's do sitting. If you're sitting on the swing, then here's the length. We're going to call it L1. And here's the person that's sitting. All right, you got it? And then so standing, so now I think what's happening is that this distance, here's like the center of mass or something, L2. L2 is less than L1. Does that sort of make sense? By standing up, your center of mass has gotten closer to the rotation axis. Makes sense? That's the difference. Nothing else has changed. And then you have to look at T is equal to 2 pi times the square root of L over G. So if L decreases, then the period should get smaller, I think.